Hello, everyone. My name is Eric Walders, and I work at Oracle, more specifically Oracle Labs, as a member of technical staff. And so, more specifically, I'm working on ML Apps team, so working on different machine learning applications and research at Oracle Labs. Okay, so in this presentation, we're going to go over how we've been able to use graphs and the power they bring for cybersecurity intelligence, and specifically in the context of one of the projects that we've been working on at Oracle Labs. So I'm not alone in this project. There's been multiple people that have been participating and working on bringing this to life. So firstly, we're going to go over an overview of what the project is. So how exactly we've defined the goals and how we've created a solution to achieve these goals. And then we'll go a bit more into the details, so the different parts that are involved in this whole thing, and after that we'll reach the end of the presentation. So what exactly is the context of this project? So at a very high level, we're just trying to analyze cloud execution logs for cybersecurity, of course. And so what this means is that we have all these different machines which are running in the cloud, and whenever they execute something, so whenever they do any kind of action, they will generate a log saying what they've done. And they could be generating thousands, if not more, of logs every single second for every single machine. So we take all these logs, and then we pass them through some kind of analytics stage. And here's where we're using the graph machine learning in the background and detecting anomalous behavior. And then once we have this anomalous behavior, we move to the investigation step. And so the idea here is that we would take what we've detected and then pass it over to some security analyst who can then do something about it. They could, they take a look at the anomalous behavior and they say, okay, this is what we need to do to respond to the incident, and then they do it, and then we're done. So we split this project into three different goals. The first one is simply being able to detect anomalous behavior. So here we're using the graph machine learning technology again. And the second is to provide some way to investigate, to look at a detected incident. So there's a whole inspection stage. And what's important here is also to be able to explain why something was actually detected. And then the third stage, the third goal, is about a response. So trying to interpret the situation, trying to suggest possible courses of action to resolve it, basically trying to help the investigator as much as possible to minimize the work they have to do to respond to any incident. So how have we created some kind of solution to this? Well, we've created a 4-stage pipeline. And the first stage is data ingestion. And this is a stage in itself because of the sheer volume of data that we have to ingest. So we're talking about billions of log every single hour. And this is equivalent to hundreds of gigabytes of data every single hour that we need to process. The second step is filtering. So what's important here is to have a fast and scalable model to be able to filter out the logs which we consider non-interesting for the cybersecurity application we're working with. And then we have a third stage. So this is the actual detection step. And so this is where the graph machine learning technology comes in, and we find the actual anomalies. The fourth step of the pipeline is the investigation step. So being able to visualize the incident, visualize it as a graph, and then be able to explain exactly what someone is looking at. And this could also include the response side of things, so the suggested actions to follow up. So now we're going to go into the specifics of each of these 4 stages, these 4 steps, starting with the data ingestion. So before we talk actually about what the data is, we need to define what we're trying to detect, what we're looking for. And so as I said before, we're looking for anomalous behavior. But in practical terms, what this means is anomalous sessions. And so what is a session? In essence, it's when somebody or some machine, it could be an automated process, connects to a machine. So they connect to a machine and then they run whatever they want. Maybe they're reading a file, maybe they're writing a file, who knows? And then they disconnect. So all that sequence of events from a single connection is considered as one session. And what we're trying to detect in these sessions is which ones are anomalous. And so anomalous session is quite similar. It's just that during the execution, there's going to be something malicious inside. And so either they're trying to do something they shouldn't, which we need to detect, or even worse, they've succeeded in doing something they shouldn't, which we also need to detect. And so this could be, for example, installing a virus, performing some kind of privilege escalation attack, or really any kind of attack that you could think of on a machine. Now, another thing to note here, which is quite important, is that this malicious execution could be hidden within a lot of normal behavior. You could connect to a machine, do your reading of files, do some very normal stuff, then try and install a virus, and then go back doing some normal stuff to try and hide that you did something that you shouldn't. And so, of course, we need to still detect this. We need to detect, the malicious thing, however you try and hide it. That is the main idea. So, okay, now what is the data we have access to? So these logs that we get from the cloud machines are actually just events. So whenever something happens, for example, if you execute a system call, if you're executing a program, if you're opening a file, or so on, then a log is generated. And so at this level, we have information on the event itself. So when it happened, we have some kind of timestamp, we know what happened, we know where it happened. But these events, these system calls, for example, can be grouped together to form processes. And a process could be running tens, if not hundreds, if not thousands of different system calls just by itself. So we group these together at the process level. And here we have some extra information at this level. So we know, for example, what command the process was trying to execute. We know from where it was trying to execute, in which directory. But so, all right, we have all these processes, and then we group them together again by connection. So if they all originate from the same connection, we group them together, and then at last we get to a session. And so at this level, again, we have some more session level information. So this would be, for example, which machine it is running on, where this machine is located, and any kind of information at this higher level. Okay, so we've got the data. We ingest the data. What's the next step? The next step is the filtering stage. So the goal here we have is to decrease the amount of data we need to consider. If we jumped directly to some graph machine learning model, the problem is that because of the sheer amount of data, it would take either way too long to process everything, or it would require too many resources, and so it'd be actually very expensive. And so one thing to note is that as we're doing anomaly detection, we know that there's actually a large amount of this data which will not be anomalous by definition, and so which doesn't actually interest us. So if we can have some kind of fast, some kind of simple method to eliminate a large percentage of this non-interesting data, then we'll be able to do something more computationally expensive with what's left. And so in this step, we're focusing on two different metrics. The first one is recall. So what's very important is to not miss any attacks. So as long as we capture all the attacks, then we can capture some normal behavior that's all right, because we're not trying to be perfect here, just trying to filter what we can. And the second metric is specificity. So this is just how much data can we get rid of. So as long as we have high recall, so we get all the attacks, then we try and filter more and more in this stage. All right, so how exactly do we do this? So more implementation details. So we've decided to take just a few pieces of information from the data to keep this simple, to keep this fast. And what we've taken is some system call information of the session, some kind of ordering information, and some kind of process information. And then we pass it through a transformer model. So this transformer model we have has been trained to predict what is normal behavior of a session. And because it has been trained to do such, what we can do is that we can give him a session and hide a few of the system calls. And then we can ask him, can you predict what should have happened? And the model will predict what should have happened based on what a normal session would have done. And so from this, we can get some kind of reconstruction error. So what is a reconstruction error? Well, it's basically how close the model got to the truth. If it was very close, then we have a very low reconstruction error, and so the session itself is quite predictable. And a predictable session is not anomalous, basically by definition, so we know that we can ignore it. Now, on the other hand, if the reconstruction error is high, then that means that it's unpredictable. Now, this might not mean that it's doing anything that it shouldn't do, but it means that maybe it's worth looking into it further. And so we keep these sessions, and these are the ones which we pass to the next stage. Okay, so what are the results we get from this? So what we've managed to do is that we've managed to filter out 85% of the original data of the original sessions as evidently normal sessions. So we know these ones, there's no risk of something bad happening in those. And then in these 15% that's left, so these potentially anomalous, we're not totally sure, but we know there's the attacks, if there are attacks, will be in this section. So with only 15%, we can do more powerful computations because we have less data to deal with. And this brings us to the third step, the detection step. So now that we have a lot less data, we want to do the actual detection. And here we want to focus on precision. So we want to be sure that if we say something is an anomaly, then it is. And this is very important because we don't want to waste the time of a security analyst. If a security analyst is given a session which turns out it's actually normal, then that's time wasted for him. And that's something which we need to avoid. Right. So this is where the graphs come in. And we've decided to represent this data as graphs for two different reasons. Firstly, because a graph can show the whole behavior of a session. And so what's important in an attack, or even just in a normal session, is how the events interact with each other. Because a single event in isolation might not be an attack, but combined with some things which happened before, some things which are happening afterwards, together this might be actually an attack. And so we need to detect these problematic combinations actually of events. So given the data that we've grouped together as explained into processes, we can create nodes for these processes. And we also have a bit of extra information we can extract from the logs. For example, what files the process is accessed, what ports they use, and maybe what external machines they connected to. So this is an example of what one of these graphs would look like. So here we have some processes which will spawn other processes, which will connect to some files, use some ports, connect to some IPs, and so on. So this is just a small section of an actual graph, because an actual graph could have hundreds, thousands of processes in just a single session. So given that we have now these graphs, we use three different techniques, machine learning techniques. The first one being graph sage, then virtual nodes, then deviation networks, which I'll get into. And at the end of all this, what we get is a single anomaly score which is generated. And this anomaly score just tells us, is it anomalous or not? Okay, so what's the actual graph machine learning in here? The first technique we use is graph sage, as I said before. And this is actually the main graph machine learning technique that we're using in this whole detection stage. And the point here is that for every single node, so let's take, for example, a process node. Let's say this red node here is a process. It will look at its neighbors. So for example, it created this node, and this node accessed some random files. Maybe it accessed a machine through here, and so on. So it will fetch information from its neighbors and gather it to itself. So here we're aggregating all the information inwards. So the information comes back to the center node, and then the center node uses all this information and its own information to create some kind of representative vector. So a representation for what this node is, taking into account the whole context in which it is. So that's the graph sage step. And so why do we use it? Because we need to combine the structural and feature information together. because one of those on its own would not be enough. But we have a problem. The problem is that every node has its own representation. So every process would have its own representation. And what we're interested in is being able to say if the whole session itself is anomalous or not. And so for that, we use virtual nodes. And virtual nodes, in essence, it creates, well, a virtual node into the graph, and the representation generated for this node will actually be a representation of the whole graph itself. And so that means that after we use virtual nodes, we will have a graph level, a session level representation. So now, quite simply, we can just take this representation and classify it or give it a score based on how anomalous it is. And here we use a deviation network loss technique, which is optimized for anomaly detection. And that one, what it does is that it puts a high score to anomalous sessions based on some normal probability distribution. And so if we have a high score, we have an anomaly. So at the end of this stage, what do we get? Well, we get that actually over 99%, so 99.9% of the sessions are still benign. Even though they were a bit unpredictable in the filtering stage, it turns out that it's nothing dangerous, nothing we should really care about. And then we detect 0.1% of these sessions which are left are actually anomalous. And anomalous in the sense we're looking for, so malicious, doing something which, well, they shouldn't be doing. Okay, so we've got these detected sessions. Now what do we do? Well, we move to the investigation step. And the first thing we do is to try and explain why the session was flagged as anomalous by the GraphML model. And this is very important so that you can actually trust the model, because we have this complicated model which maybe we don't know why it said something is anomalous, but if we can have proof that it's right, then one, we can trust it better, and two, we can actually use that information in a better way. Right. So, okay, how do we get this explanation? So what we take is the flagged session previously, and then we use a new model, which is called a graph neural network explainer model. And what it does is that it explains why another model thinks something. So here with graphs, what it does is that it says, in this session, in this graph, this is the critical section which makes this session anomalous. So it's going to learn a small subset of the graph and really be able to focus on that area and say, this is the problem here. Now, after this, we also get information on which subset of features are important. So we get two different things. We get small graph and a small set of features which should be looked at. So, okay, we generated this explanation. And what do we do with it? Well, we need to be able to have an investigation by a security analyst. And so we do this by providing a platform where a session can be visualized as a graph and explored dynamically. And the explanation we generated before is integrated into this graph. And so it will tell you as you're looking through it, this node here, this process here is actually very important. You should look at it more carefully. And so that gives you a way to, a starting point to know what the session is doing. But we can also provide more pieces of information. For example, we can base ourselves off previous attacks. We can say, well, this session here we've detected is actually similar to this previous thing that we saw in the past. And so, yeah, you can guess what this new flagged session is trying to do based on what the previous one was trying to do. And not only that, we can also say, well, look, this is how we resolved it last time. These are the actions that were taken. So what you can do most probably is take a similar set of actions and resolve the incident. So there we're trying to simplify as much as possible the work for the investigator. Right. So now we've gone through the four different stages of our project. So from data ingestion, where we have millions of logs, down to filtering, where we get rid of 85% of them. Then we detect the actual anomalies, which turns out to be an extremely low percentage. And then we give an investigation platform um, to understand what's going on. Okay. So this project and the work that we've put into it is still ongoing, and we're still learning as we're progressing through it. But there are quite a lot of challenges we've identified, and which have to be taken into account. So firstly, the data size itself is huge. And this means that performance is actually a necessary part of the whole pipeline. Because if we have the pipeline which runs and which takes more than an hour to process an hour of data, then that means it's going to be late to process the next hour. And so the delay is going to build up, and then that's going to cause issues. So we need to have a very performance pipeline. And not only that, we have that the data size itself increases over time. We have, more and more applications and machines are going to the cloud, and so we will have more and more data, and so we'll have to be able to tackle this challenge. The second point is about the attacks themselves. So attacks actually, well, they change over time. There's new attacks that get discovered. There's new ways to do malicious things on machines. And what we need to do is we need to be able to learn from new attacks and then be able to learn how to detect them in some kind of automated manner. And we also have that while the attack environment itself is also dynamic and evolves over time, and so we must make sure that a system can adapt to these changes. And by being able to continuously learn, what we get is a system which is actually a lot more powerful than the current rule-based systems that are being used today. And so we plan to make this available to SaaS services in the cloud, and while we believe this will be a huge asset to provide the next level of security. Thank you for listening. So this was quite a high-level overview of the project. So if you have any questions, doubts, or just want to discuss something with us, then we'll be happy to respond. Just feel free to contact us at the addresses below. Thank you.